Hello, welcome to today's video where we're taking a look at exponential growth and decay, or in other words, wordy-based questions involving the number e. But before we begin, I do need to give you a bit of a warning, which is that you might hear the terms exponential growth and decay being used in everyday language, but actually incorrectly, because sometimes people say, oh, this thing is increasing exponentially, and they're saying that to add a bit of drama to what they're saying, but they basically mean that it's increasing really fast, but in reality that's an incorrect use of that term, because something growing exponentially or increasing exponentially is actually related to a very particular type of equation, a very particular structure. Admittedly, in the real world, there's lots of different ways you can then rearrange that structure, so there's lots of different formats that the scientific world might call exponential growth, but the very particular structure that we're going to be looking at for the purposes of Maths A-level is where we define exponential growth as being an equation of this format. You'll have the output variable equals to a lots of e to the power of k lots of our other variable. In this case I've written as an x. The x and the y, as I said, are variables. The a and the k are constants. So that means the a and the k are values that are set in stone before you start actually using the equation to model whatever it is you are modeling. And then when it comes to exponential decay, well, it's going to be a very similar equation to what we have for exponential growth, except because we're now modeling something that's decreasing over time, then therefore what we do is we put an extra minus sign in the power. So therefore it's worth mentioning in both of these cases the k is a positive number, because even for exponential decay I've already taken account of the minus sign before writing the k in the power there. Okay, so that's the maths side of things, but we also need to be watching out, as these are wordy based questions. There's certain words we need to be looking out for in those words to know what it is we're meant to be doing. One of those keywords is the word initial, because if you see the word initial, it basically means at the beginning, and so therefore if we're talking about numbers, that means the time is equal to 0. So that's the first thing to be aware of. The second thing to be aware of is that you might sometimes see the word rate, and you need to be aware that actually rate is related to differentiation. Rate of something is the derivative of that thing, and generally we're differentiating with respect to time because that's how things change. They change over time, so that's the sort of thing we're talking about here. Cool, but therefore, wait a minute, we're differentiating things involving e, or specifically e to the power of something, and the problem is, you might not know how to do that, so a quick little pointer in case you don't know how to differentiate things of the format e to the power of x. The first thing to be aware of is don't just multiply by the power, because that only works when you have x to the power of something. The crucial thing there is to point out that the variable, the x, is in the base, and then the power is fixed, whereas when we have something like e to the power of x, e is a number, so the base is now fixed, and it's the power that's the variable. So because that structure is different, that's why the rules for differentiating it are different from what you came across with polynomials. However, when we try to differentiate e to the power of x, it differentiates to, well, itself, e to the power of x, which is really cool and really unique because usually a lot of the time when we differentiate things, the expression changes as part of that differentiation process. But not when we differentiate e to the power of x, it just stays as it is. And this has really interesting and important repercussions as to why we care about this seemingly horrible decimal that's represented by the letter e. It's because there are lots of things in the real world that have properties related to the property you can see on the screen right now. And that's because, a reminder, differentiation means you're modeling the rate at which the quantity of something is changing by. And therefore, if the rate at which the amount of something is changing by is related to the amount of that stuff you currently have, that is then lining up with things we observe in the natural world to do with populations of natural things. Because if you're looking at plants or animals and the populations of those things, the amount of babies, that's how much those populations are generally changing by, is always going to be related to the numbers of those animals or plants that you currently have. For instance, if you're looking at a colony of rats, the more rats you have, or the more adult rats you have, I should say, the more baby rats that are going to be created as a result of that. So therefore, that's why this stuff is so important. But we're not just going to always be differentiating things that are just e to the power of x. So something to be aware of is, as usual, if you have a number in front of an expression you're differentiating, that constant in front doesn't really affect things. However, if you have a constant in the power in front of the x, that does affect things. Again, reiterating that you don't just multiply by the entire power, but there is going to be something to do with multiplying to do with the power. But what you're going to do is just multiply by the number that's in front of the x in the power. In this case, I've used the letter k as a placeholder for that. But therefore, let's take a look at some examples of that. But just be aware that this is a fact that you're going to need to know off by heart to be able to quickly differentiate these things. Differentiating e and other more complicated stuff is something you're going to explore later on in the course more. But for the moment, this is just a fact you need to know off by heart. So, looking at our examples, the first example, we're differentiating 3 lots of e to the power of x. As I said though, the number in front of something doesn't affect things, so you've got to almost view this as 3 lots of e to the power of x, because that is what it means by the order of operations. But therefore, the e to the power of x just differentiates to e to the power of x, and then we've got 3 lots of it, so it just differentiates to itself. This time though, for the second one, we're now differentiating e to the power of 8x. So therefore, the 8 isn't in front of the e, it's in the power in front of the x. And by the rule I just said on the previous screen, we need to basically multiply by that number as part of differentiating this expression. So we're going to get 8 lots of e to the power of 8x. In other words, whatever number you see in front of the x inside the power is what we multiply by as part of differentiating these things. Not the entire power, just that number. And then also as a reminder, putting it all together, a reminder that different expressions separated by plus or minus symbols can be differentiated separately. So then if you're differentiating things like 6x, you're just using the other rules you've previously learnt to help you differentiate those sort of expressions. So therefore, to differentiate first of all, individually, the 9e to the power of 4x part, well, that is the situation that we've just been doing above. We've got the 4 in front of the x, so as part of differentiating, we have to multiply the front, the coefficient if you will, by that number 4. So 9 times by 4 is 36, and then the e to the 4x part stays as e to the 4x. So we just multiply by the number in front of the x, and then the e bit stays the same. And then added onto that, the derivative of just the 6x part differentiates separately. And 6x just differentiates to 6, something we learned before. So there we go, that's how you differentiate things involving e to the power of something. Okay, so we've done a lot of talking so far, but that's just to embed the skills we need. Now let's apply that to some wordy questions. So here's our first word-based scenario. So they're describing the fact we've got the radioactive decay of some element, and they've given us the equation. So luckily, because they've given us the equation, we can just accept that that's what we're using, and we've just got to use that as part of the question. We've also been told what the variables are. It's always important to highlight those to yourself, because you sometimes can get caught out in questions by what units they're using or wanting you to give in the answer. In this case, the mass is in grams and the time is in years, but therefore if the question suddenly wanted the answer in kilograms, obviously be paying attention to that and be aware you need to obviously change the units as appropriate. But anyway, going on to part A, we need to find the initial mass of this element, and the key thing to be aware of is we're noticing that word initial. As I said before, the word initial means the time is equal to 0. It's at the beginning of whatever it is you're looking at, so no time has elapsed yet. So for part A, I'm going to cram into this little bit up here on the screen. All we've got to do is plug t equals 0 into this expression. Now, a big mistake that a lot of people make when plugging 0 into things is they just start getting into lazy bad habits and just assume if you plug 0 into anything, it's always going to become 0. But it doesn't. In this case, because the 0 is in a power, we have 0 times by minus 0.767, which does become 0 in the power. But then because the 0 is in the power, anything with a power of 0, except for 0, will just become 1. So we got 4 lots of 1. So the answer is, initially, there are 4 grams. So something to bear in mind, because these are wordy questions, your answer should relate back to the wordy based scenario in your answer. An easy way of doing that is just, instead of writing a number, making sure you're always writing the units so that the number actually has meaning. They know what they're talking about when we see it. But sometimes you might have to write a sentence to fully answer whatever it is they're asking you to do. On to part B, we've got to find how long it takes the mass to become 1 gram. So therefore they're telling us for this question that m is equal to 1. So therefore we've just got to plug 1 into the equation and then find what t is. And therefore ultimately this is just using skills we've seen in previous videos to do with logarithms. We want to isolate the e part so that we can use a logarithm. So I'm going to first divide both sides by 4 to get this. And then we're going to use logarithms to then deal with the fact we've got the unknown variable in the power, which is not a nice place to have an unknown variable. Of course, because our base is e, instead of using log base whatever, we're going to be using ln, although that is technically just log base e. So therefore, we end up with minus 0.767t is equal to ln of 1/4. Now, ln of 1/4 is something you can just type into a calculator. It will be a number, but I'm not going to bother doing that yet. It's easier to keep things in exact form for as long as possible. It takes less writing out. It takes less typing into the calculator multiple times. We can just do it later at the end. Because I now realize if I want to find t, I've now got to divide both sides by minus 0.767. So therefore, t is equal to minus 1 over 0.767, lots of ln of 1/4. And therefore that will get us 1.81 to 3 significant figures. A reminder, for Maths A-level, the default rounding is 3 significant figures, unless the question says otherwise. But as I said before, good to put context to your answer, so I'm going to make the point that it's 1.81 years. I mean, you could even go really overboard if the question asked and convert that into years and months, but the question didn't ask, so I'm not going to bother. And then for the part C, which I'm going to cram to this tiny space over here, we need to find the rate at which the mass is decreasing after 3 years. Now, rate just means differentiating. Because they're saying decreasing, that means we already know what sort of number we're expecting our answer to be when we do the differentiation. We're expecting a negative answer for what we get when we differentiate. But we're not just going to be differentiating, we're going to be plugging in t equals 3, because we're not just finding the general expression for the rate at any given time, we're finding the rate at specific t equals 3. So, first thing we need to do is differentiate. To differentiate the expression we have, first we'll get the notation right. It'd be dm over dt, because we're differentiating the t's, and the expression is of the form m equals. That is then going to equal what we get when we differentiate this stuff, which, as a reminder, means we're just going to look at the number that's in front of the t, in the power of the e, and we're going to multiply the front, the coefficient of the front, by that amount. So minus 0.767 times by 4 lots of e to the minus 0.767t. So that's what the derivative is. Of course, again, you could combine the 4 and the minus 0.767 by multiplying them, but I'm not going to bother because I know we want what dm over dt is at specifically t equals 3. So now I'm just going to plug t equals 3 into this expression. And plug it into a calculator to find out what that's going to become, which is minus 0.307 to 3 significant figures. There could be an argument made about whether we need to include the minus sign in our answer, because it was asking us for the rate at which it is decreasing, and therefore that minus sign is just to tell you that it is decreasing rather than increasing, and it's the number afterwards that's telling you how much it's decreasing by. So that's something to bear in mind. In this case, I don't think they would care about units so much for the derivative, but for your interest, the units of the derivative are related to the units of the variables before we differentiated. So therefore, it would technically be grams per year if we're being fully accurate in what we're saying there. Okay, that's the first example done. Let's go and look at a second example. And the interesting thing about this example, when you read about it, is they're giving us a scenario involving a colony of moles, but they tell us that the colony of moles is growing exponentially. And that's all they say. They don't give us an actual equation this time, they just say it's growing exponentially, which appears quite vague, but certainly in Maths A-level, you are allowed to, if they don't give any more detail than that, assume that they mean we're dealing with a particular model where it's of the form a, e to the k, and then the variable we may as well use in the power would be time, because you'll notice later in the question they're talking about time. I'm also going to use the letter m again, but this time I'm going to use the letter m to represent number of moles rather than mass that we had in the previous question. However, for the moment, after reading the first sentence, that is all we know about what's going on with these moles, because we don't know the value of the constant a, and we don't know the value of the constant k, except that we know k should be a positive number, because they're telling us it's growing exponentially, rather than the number of moles decaying exponentially, or decreasing exponentially. So, therefore, the way we're going to find the a and the k is we then got to use the information given the question. They tell us that initially, so time equals 0, there are 100 moles. So therefore, we know when t equals 0, m must equal 100. So therefore, we can go ahead and already start to use that fact in our equation to start to find out what's going on. If we plug t equals 0 and m equals 100 in there, we get 100 equals e to the k times by 0. However, just like before, if you have anything times by 0, it becomes 0. And then, if you have a power of 0, it's just 1. So therefore, that already tells us that the value of a is 100. Therefore, actually something interesting to note that I didn't talk about before is actually that's all the value of a in these models ever is. If you've got an exponential growth or decay model exactly of the format we can see right here, then the value of the a is the initial amount. But if you forget that, it's fine, because the numbers will generally show that to be the case anyway. The second key bit of information is that they tell us that after 2 years, so when t is equal to 2, there are 225 moles. So if we take time to be measured in years, then therefore t would be 2, and therefore m is 225 at that stage. So therefore we set m to be 225. We now know the value of a, so I'm not going to write a, I'm actually going to write 100 in place of it. We have ae to the k, which we still don't know the value of, lots of t, and this time we have 2. So 2 times by k would be 2k. All we've got to do, therefore, is now solve this equation to find the value of k. So therefore, just like we were in the previous question trying to do, you want to isolate the e. So I'm going to start by dividing both sides by 100. And then we can, although that fraction could be simplified, I'm not going to bother. The calculator will simplify it for me later. I am going to use logs to move that unknown thing to not be in the power anymore. So we get 2k is equal to ln of 225 over 100. But then, of course, if you want k, it's just going to equal half ln of 225 over 100. Something to be aware of, always pay attention to how they want the final answer given. Do they want it given in exact form or as a decimal? If they want it in exact form, I would be having to simplify the fraction that's inside the ln, which wouldn't be too difficult to do, but you would have to actually remember to do it. But alternatively, this time they have asked to give it as a decimal, but do pay attention to the level of accuracy or precision that they want you to give the answer to. So in this case, they've asked for 4 decimal places, so obviously make sure you have done that. The last thing is, though, pay attention to what the question asks us to do. A lot of students will just get to this stage of the question and think they're done and move on, but we haven't, because if you read it, you'll realize they've asked for an equation of the model, which we sort of did before when we wrote this, but that actually wasn't the final answer because we hadn't found the value of the a and the k. So the final answer is to rewrite that equation, but now with the values of a and k written in their respective places. So we know a is 100, we have e, then we've got k, so we've got to actually work out the value of that as a decimal, which is 0.405, and it would be a 4, but because there's a 6 after it rounds up to become a 5, and then we've got the t. So therefore this is what it is, and therefore we've obviously rounded to 4 decimal places for that power, for the value of k I should say, as they asked. So that's how you ultimately deal with context-based questions involving exponential growth and decay. However, before we go, there is one more thing I want to talk about, which is a particular type of question they sometimes ask as part of this stuff, which is basically the long-term predictions predicted by the model that we're using. In this case, an exponential growth model or exponential decay model. But either way, what does the model predict? How do we deal with these sort of questions? Well, first of all, to get an understanding, we need to know what they're asking. They're basically asking what's going to happen for very big values of time plugged into the equation. And so therefore, actually, a way some students have of dealing with this stuff is a bit cheaty, but it does work a lot of the time. You can just take a really, really, really big number and then replace t with that number and just see what happens. However, that is a bit cheaty and lacks sort of some of the understanding really behind what's going on. So there is a more mathematical way you can go about really seeing what's going to happen in the long term, and it's by ultimately drawing a graph. Because once you've drawn the graph, all you've got to do is look what happens as you look at really big values of t, which is to travel to the right along the horizontal axis, because that's where the big values of t are going to be, and see what happens as you approach a really big value of t, what's going to happen to the y value. I've used y, obviously that's a placeholder, whatever variable is the output variable. See what happens to that as you travel to the right on your graph. Ultimately, because some of these things are more complicated looking graphs, therefore you are going to want to make use of your graph transformations knowledge from earlier in the course. So a couple of quick examples. Again, I've given a context, but it isn't really important. Ultimately, we've just been given two models, and we want to know what the long-term prediction is according to these two models. So, to give us a bit more room, let's just first focus on model A. So for plant A, it's modeled by the equation we've been given, and we want to determine the long-term prediction. So the best way to do that is draw a graph. Now, to be able to do this, you're expected to know what the graph of y equals e to the power of x normally looks like. Y equals e to the power of x is a graph that normally looks like this, if I do a quick sketch. It's something that's got what we call a horizontal asymptote of the x-axis, and then it basically just curves up as you travel to the right. So therefore it's a graph that increases the more you increase the value of t. So how is that going to be useful here? Well, we don't have e to the power of x, we've got a t rather than x, but that of course just changes the label for the axes, but we do have some extra numbers, and those are graph transformations. The 6 in front is just a stretch scale factor 6 parallel to the y-axis, so therefore the graph is going to look a bit more stretched vertically, but it's still going to have the same rough shape that it had before. In other words, as you travel to the right, the graph is going up. And then similarly, the number in front of the t in the power, because that's not happening in front to the entire thing, it's an x direction transformation. So that's a stretch scale factor 1 divided by 0.3 parallel to, in this case, the t-axis rather than the x-axis, but same thing, horizontally stretched, scale factor 1 over 0.3. So therefore, ultimately, that again is still going to roughly maintain the shape we have before. It's just going to look a little more stretched out. So therefore, the graph of what we're looking at would look something like this. We'd have the t-axis, we'd have the n-axis, and therefore the graph will look something like this. Terrible drawing incoming. There we go, something like that. And so therefore that's important because it means, as you can see, as we travel to the right on the graph, we can see it's just going up and up and up forever and ever and ever. So therefore the long-term prediction for the number of plants for plant A using this model is that as time increases, the number of plants will increase forever. It's worth pointing out, if we're talking about posh mathematical notation, what we're effectively saying is that as t tends towards infinity, then therefore n tends towards infinity as well, but that's really sort of stuff you're not really having to write, so I wouldn't worry about that sort of stuff, but just in case you see that in a book written at some point, that's what we're talking about. Okay, so terrible handwriting aside on what I wrote on the screen just then, let's go on to Model B. So, once again, how are we going to see the long-term prediction? Graph transformations. So, there are more graph transformations that are happening this time that we need to be aware of. Something I like to point out is that for some people it might be beneficial for them to view this equation written in a slightly different way. Instead of 20 minus e to the minus t, it might be beneficial for them to view it as minus e to the minus t plus 20. And that's because it then makes it more clear we've got three main graph transformations happening to e to the power of t to get the graph we are trying to draw here. There has been a reflection in the y-axis. It says in the y-axis, but that means a horizontal reflection in other words. So therefore that's going to take our graph that we'd normally have for e to the x, which looks very roughly something like that, and we'll now make it become something like this, basically back to front. So something like that. So that's a terrible drawing, but hopefully you get the idea. Flipped round the other way. Shouldn't use the word flip though, reflect is the proper terminology. And then also this minus here means a y direction reflection, which is not how we say it. Officially, it's called a reflection in the x-axis. So therefore, that's going to change it as well. It means we're now going to have that graph we'd already reflected once, reflected again, which means we're going to end up with this. But despite doing two transformations so far, the asymptote is still in the same place. It's still the x-axis, and that's because y equals 0 was not affected by the reflection in the y-axis because that's a line that's symmetrical about the y-axis, and then y equals 0, in other words the x-axis, is then also not affected by the reflection in the x-axis because if you reflect anything on the mirror line, it stays in the same place. So that's what we've got so far, but the last thing we need to deal with is the plus 20, and that's a translation of 0, 20, so we're moving up our graph 20 units. Again though, translation is the official proper terminology, so therefore the graph moves up, but not only does the graph move up, also the asymptote moved up 20 units as well. So therefore I'm putting a dotted line in to show where the asymptote now is. It was at a y-coordinate of 0, so now it's going to be at a y-coordinate of 20. The impact of this is it means now, as we travel to the right on the graph, we can see it's now not going to travel up forever because the graph is now heading towards its asymptote. So therefore, the long-term prediction for this model is that as time increases, then eventually the number of plants is going to approach 20. So therefore, in the long term, the model predicts that there will be 20 plants. So we'll just write that. In the long term, the model B predicts there will be 20 plants. Again, terrible handwriting, I'm very sorry. But there you go, that is how to answer those questions as well. And that is all I wanted to cover for this video. Hopefully you found this useful for knowing how to deal with wordy exponential growth and decay questions. Sorry if this video was a bit long, but hopefully it has been useful. And I will see you in a future video for some more maths.